So the last step of the previous lesson was that the relative permittivity in the case of the electron system is equal to 1 plus k0 squared divided by q squared. At this point, we may recall the equation that relates the relative permittivity and the actual potential to the external potential. At this point, the external potential in the Coulombian approximation, so phi external, is proportional to 1 divided by q squared. The idea is to find the actual value of the potential into the system. So phi of q is equal to the, sorry, I just write proportional because here I wrote proportional. So phi of q is proportional to the external, no, this case, sorry, here there is an equal. The external divided by the relative permittivity, and this is 1 divided by q squared times 1 divided by 1 plus k0 squared divided by q squared. And that is equal to 1 divided by q squared plus k0 squared, because this q squared here gets simplified by this q squared here. What happens is that now we have a Fourier transform of the actual potential into the system that for, in this case, if we consider the limit for q that goes to 0, we have 1 divided by k0 squared. So this is different from infinity, as we had using the external value, so the actual value of the external potential. So the contribution of the rearrangement of the electrons removes the divergency of the actual potential into the system, as now we have a constant term for q that goes to 0. In particular, it is interesting to see what happens if we move from the Fourier transform to the direct space representation of the actual potential. In this case, the direct space representation is minus e divided by 4 pi 0, 1 divided by r times e to the minus k0 times r. So we have, let's say, the vacuum expression, that is the first part, times an exponential contribution. And this is called the Yukawa potential. And Yukawa comes from a similar potential that you have in elementary particle physics. So there is a potential that has exactly the structure that is used in elementary particle physics that is due to Yukawa. And in this case, you may call this as a sort of screened Coulomb potential. And if you notice here, when due to the presence of this exponential term, the long range of the Coulomb potential is strongly depressed, as when, so if R0 is larger by 3 times 1 divided by k0, and due to the fact that r times k0 comes from this expression, so k0 has to be for what concerns the units of measurement has to be a wave vector. So K0 times R has no dimensions. So K0 is meters to the -1. So 3 times 1 divided by K0 is a length. So if R0, sorry, if R is larger than 3 times 1 divided by K0, then we expect that the value of the potential can be considered 0, negligible. So at this point, the question is, what is the value of K0? It can be seen that K0 is of the order of Kf. And Kf, let's say, in a cubic crystal, is of the order of 2 pi divided by A. So 1 divided by K0 is of the order of A divided by 2 pi. So 1 divided by K0 is a length that is of the order of the lattice spacing, more or less. So if 3 times a length of the order of the lattice spacing is enough to completely, let's say, depress the contribution of the interaction potential, this means that the capability of the electrons to screen any external charge is quite strong, because, let's say, if you are, let's say, 10 nanometers away from the external charge, then you do not see any effect of that charge, because the effect of that charge is damped to 0, quite close to the charge itself. And you may apply the same the same result to any of the electrons that belong to the system. So the effect of any charge is quite fast screened by the cloud of electrons that you have in the system. So at the end, the range of interaction of the inter-particle interaction in the system is not infinite as in the pure Coulombian term, but it's quite short due to the presence of this Yukawa potential. So this is, let's say, if you know that, this is an information that is quite in favor of the fact that the actual contribution of the electron-electron interaction into the system is not as important and as one may expect just considering the pure Coulombian potential. So thanks to the fact that the actual interaction potential is the Yukawa one, so the screened one, not the pure Coulombian potential, then the electrostatic effect of the electron-electron interaction or electron-ion interaction is strongly depressed with respect, again, to what you would have observed in vacuum. And this is also another, let's say, another consequence. So let's suppose that you are that you have an infinite solid. For the moment, I have always made the calculations concerning infinite solids, because the Born-von boundary conditions are not conditions that tells us what is the behavior of the surface. Those conditions just tell us that we want to have propagative solutions of the Schrödinger equations, and so we transform the solid into a three-dimensional torus. So no effect of the surface is included in, no actual effect of the surface is included into the Born-von boundary conditions. But if you consider the surface, so let's suppose that here we have, just to make an example, here we have the solid, and here we have vacuum, or air is the same. So here you have a solid, here no solid. And you have this surface. On one side of the surface, on the left side in this picture, you have the ions, the electrons, all the things that you have in the solid. On the right side, you have nothing. nothing, let's say, or air particles or no particles if you are in vacuum. So the surface is a strong modification to the ionic potential and also to the electronic potential, because you have a strong deviation from the symmetry, periodicity that you have on the left side. But if we take into consideration the screening contribution of the electronic charges, then if you stay here, so if you're supposed to be here and to look at the system, and if the distance, if this d is larger than 3 times 1 divided by k0, then you don't feel the effect of the surface, because the screening, let's say the surface is not actually an additional charge, but is the removal, let's say, of all the ionic charges, electronic charges that you have after that surface. So here you have a strong change of the electronic density charge, ionic density charge. So here you have a strong modification in the system. But what is the effect of that modification on the behavior of the solid state? That modification is not felt for meters, not for centimeters, but is felt for nanometers. After those nanometers, the effect of the modification disappears. So that's why at the beginning of the lessons, I told you that I will have always assumed that we are in an infinite solid and we neglect the contribution of the surfaces. Because if the size of our solid is larger than a few nanometers times a few nanometers times a few nanometers, then within the solid, the particles that we have within the solid do not feel the effect of the surfaces. So due to that, thanks also to this screening effect, we may actually consider that any solid, any, let's say, macroscopic solid, can be considered as an infinite system due to the strong depression of the effect of the surface over, thanks to the charge redistribution. And thanks to that, again, the effect of the surface is restricted only to the first nanometers starting from the surface. Only when you consider nanostructures, so systems whose lateral size is of the order of nanometers, then you may actually expect that the properties of those structures are strongly affected by the presence of the surface, because the surface also modifies the electronic orbitals. So you have a strong modification on the properties of the electrons, ions into the system. So that hypothesis that the hypothesis that I told you at the beginning of that I described to you at the beginning of the lessons, was also based on the assumption that thanks to this screening, the actual contribution of the external potential is not as strong as one expects to observe. So at this point, we may do exactly the same calculation that we did concerning the evaluation of the exchange integral, but replacing the Fourier transform of the pure Coulombian potential with the Fourier transform of the Yukawa potential. So at this point, we may do something like this. Start from the exchange energy contribution and evaluate that using the Yukawa potential. So at this point, the summation, the starting point of the calculation, where we had the summation over 1 divided by m minus k squared, is replaced by the summation over m of 1 divided by k0 squared plus m minus k squared. So if we make the calculation re-evaluate the exchange energy, and let's say if we try to as the problem was the Fermi velocity, because without the Yukawa potential we have a divergency at the Fermi energy. So the main problem is it possible to evaluate the Fermi velocity? The answer is yes. And if you evaluate the Fermi velocity with the interaction, you find that the Fermi velocity is nearly equal to the Fermi velocity that you have for free electrons. So the conclusion is that if you replace the Fourier transform of the Coulomb potential with the Fourier transform, and you make the calculation again, then you find that the divergency disappears. So that was the Coulomb potential was actually the source of the divergency. So you're able to evaluate the Fermi velocity, and what you find is that is nearly equal to the free electron value. The difference is of the order of a few percent. So the conclusion you obtain is that within a few percent, with a small percentage of with a very small percentage of approximation, the velocity of the electrons at the Fermi surface is not affected by the fact that we consider the electron-electron interaction. So this is quite an important point, because again, even if the electronic density is huge, because we have a number of electrons that is of the order of 10 to the 28 electrons per cubic meter, then we have that the Fermi velocity is nearly unaffected by the electron-electron interaction. And a great contribution to this result is given by the screening. So the screening, that means the fact that the relative permittivity is given by this expression, gives a strong contribution to this result. So the actual effect of the electron-electron interaction is strongly depressed. But there is also another physical motivation behind the fact that the result of the electron-electron interaction can be considered to be negligible at the end when we consider the final value of the electronic properties in the system, even if we switch on the electron-electron interaction. And just to describe what is the physical motivation, another physical motivation behind the fact that the effect of the interaction so thanks to that, we have a negligible effect of the electron-electron interaction, but there is another physical motivation behind this negligible effect. And the other physical motivation can be understood if we consider what happens when we, let's say, when we have two electrons that, due to the interaction potential, interact with each other. So if we suppose to have electron 1 and electron 2 that interact with each other, we have to expect that electron 1 will have an initial level, electron 2 will have an initial level. So we have to find two final levels to host electron 1 and electron 2 after the interaction. To describe this process, I will make, and to make the drawing simple, I will assume that we are in a condition, let's say, close to the free electron picture, but the same mechanism is fine if you consider also a situation that is not the free electron one. So let's suppose that this is the Fermi energy in the system. Now, and another hypothesis is that electron 1 is not below the Fermi energy, but is excited here at an energy that is slightly larger than EF. And in a while, you will understand why I put that electron in that position. So let's suppose that this is electron E1. Electron E1 is interacting with another electron belonging to the Fermi sphere. Yeah, thanks. So the energy increases in this way. So electron 1 has an energy that is slightly larger than EF. Electron 2 will be an electron belonging to the, let's say, to the Fermi surface, that is within the Fermi surface. So let's suppose that electron 2 is here. At this point, we need to find out two final levels for electron 1 and electron 2. And I call those levels, the final, after this interaction, I have electron 3 and opposite, and electron 4. What is the position in energy of electron 3 and electron 4? Electron 3 and electron 4 has to be found at an energy that is larger than EF, because all the levels below EF are occupied. So what I expect is that the energy value for electron 3 and the energy value for electron 4 are larger than EF, because no empty levels are found below EF. Just a comment, the fact that I may say no empty levels can be found below EF is a consequence of the hypothesis that I'm assuming that I'm working at t equal to 0. So the occupancy is 1 up to EF, and then the occupancy drops to 0 of the levels. So that's why I assume that I have no free levels below EF. No, in principle it's possible, but this is a specific, let's say, the more general assumption is that you have no final levels below EF, but you have just the final levels above EF. It's correct. In principle, 1 should take the place of 2 and 2 should take the place of 1, but you have just one specific situation. So I'm assuming T equal to 0 Kelvin. And another thing that I have to apply here is the energy conservation. So I have to say that E1 plus E2, so the energy of the initial electrons, has to be equal to E3 plus E4. Now, if you notice, since E1 is here, so in the energy scale, this is E1. E2 is here. We know that E3 and E4 have those two electrons has to stay at an energy that is larger than EF. But the question here is it possible for those electrons to stay up here? Is it possible to have this situation? If you have this situation, the sum of those two energies will not be equal to the sum of those two because they are larger than the largest. So this is not possible. The only solution is that E3 and E4 are found there in that slight portion of space in between E1 and EF. At this point, let's say at the beginning I told you, I assume that E1 is an excited electron with an energy E1 larger than EF. At this point, since at t equal to 0, let's say I expect that no electrons are found at an energy larger than EF, I have to assume that in equilibrium, I have to assume that E1, the largest possible value that I may have for E1 is EF, because in principle, no other levels are occupied above EF. If E1 has to be equal than EF, E3 and E4 has to be larger than EF. The only solution that you may have to satisfy the energy conservation is that E1 is equal to E2 is equal to E3 and is equal to E4. Because if you pick up electrons that come from, let's say, far away from EF down in the Fermi sphere, then you may not have energy conservation if you pick up one electron at EF and you expect to have the final levels free very, very close to EF. So the only solution is that all the four electrons has to stay exactly the Fermi surface. But if all the 4 electrons has to stay at the Fermi surface, this means that let's say, the volume. So if this condition has to be fulfilled, then the volume, including, the volume of the region including initial and final states is 0, because if you evaluate the volume of that surface, the volume of a surface in a 3-dimensional space is 0. So from the point of view of the interaction, you may conclude that you actually have the possibility to observe an interaction, but the volume of the phase space that corresponds to that interaction is 0. So when you try to evaluate the contribution of that scattering and you make any integral over the volume, in this case, you integrate over volume that is 0. So you have no contribution from this mechanism to the scattering. So when T is equal to 0 Kelvin, then I expect that the electron-electron interaction has no effect because, sorry, one step back. We observe the interaction, but the volume corresponding to that interaction in the reciprocal space is 0. So any integral that will investigate any integral you make to find the actual value of that contribution is expected to have a value that is 0. So what is the physical motivation behind this 0 volume? The physical motivation is the Pauli exclusion principle, because the fact that E3 and D4 are chosen here and not down here is just to the Pauli exclusion principle. Because if all the levels are occupied here below, then you may not put E3 and D4 below EF because you have no space for those electrons. And the fact that you have no space for those electrons is a consequence of the Pauli exclusion principle. So the other physical mechanism that prevents the effect of the electron-electron interaction to be observed when you consider, for instance, the final energy of the electrons is the Pauli exclusion principle. Then a partial objection is that we are not always at T equal to 0 Kelvin, because in general, So when t equal to 0, the volume is equal to 0. But if T is different from 0 Kelvin, so the temperature is higher, then what we have is that we may have possible energy values that are occupied even above EF, but due to that, we also have the free levels below EF. So at that point, you have, let's say, volume for this scattering, and the volume of this region is different from 0 because you have the broadening of the occupation distribution due to the fact that the Fermi function is not a step function, but has a variation. And this variation is observed in a range of energies that is of the order of kT. So in principle, the volume is not 0. So at this point, what happens? At this point, you may observe the effects of this scattering process between the electrons, as you have a space in the reciprocal space for the final levels. And at this point, if we have a scattering process, we may associate the relaxation time to that scattering process. And what is the relaxation time due to the interaction is proportional to what? Is proportional to the number, let's say, of scattering events that you may observe in the system. So that depends on how many, let's say, how many final levels I have at disposal for this process. In this case, the probability to undergo a scattering event depends on which parameter. If we fix E1, so if we're supposed to choose the energy E1, so E1 is fixed, then at this point, if we consider this equation, E1, let's say, is fixed. We have 1 degree of freedom, we may choose the value of E2. Another degree of freedom, we may choose the energy E3. At this point, E4 is fixed, because if we have E1, E2, and E3 fixed, then E4 is fixed. So in this equation, we have just 2 degrees of freedom. And what is the, let's say, range of variation corresponding to the choice of E2 and corresponding to the choice of E3? The range of variation is proportional to kT, because kT is the width of the range of energies where we may choose E2, the value of E2 may vary, and also the value of E3 may vary. And what is the dependence of this relaxation time over the temperature? Let's say when the temperature is 0, no scattering event. If we have no scattering events, the relaxation time has to be infinite. So we expect that the proportionality is between relaxation time and 1 over T. So the larger the value of the temperature, the larger the width of the energy range where we may pick up the variation of E2 and E3, the smaller will be the relaxation time, because if the width of that energy range is wide, then we have the possibility to observe many scattering events. And if we have many scattering events, then the relaxation time is expected to be small. And what is the power of T? We have a T factor due to the choice of E2, another T factor due to the choice of E3. So here we have a T to the power of 2, 1 over T for E2 and 1 over T for E3. At this point, to evaluate this relaxation time, we would need here a coefficient. Now, this coefficient can be found just in the text. There is a proposal concerning how to suggest the value of this coefficient, and that suggestion is made just on the fact that based on the fact that here you have a time, here you have a square root of the temperature, so you need the coefficient whose units of measurement are such that this Kelvin to the -2 that you have here is transformed into seconds, into a time. And if you evaluate that coefficient considering this requirement, what you find is that the interaction is of the order of 10 to the -10 seconds. And if you remember, this is huge with respect to the value of the relaxation time that we found in the Drude model, Sommerfeld model, that was on the order of 10 to the -14 seconds. So is it fine or not? Is it fine that we have this equation, this relationship between the two relaxation times or not? The answer is yes, because this is the relaxation time due to the electron-electron interaction. What is one of the assumptions that were made during this calculation? If you remember, the main assumption was, let's suppose that the system can be still described by single electron levels, because the Slater determinant was a combination of single electron levels. We just arranged all the levels to say, okay, let's build up a wave function that is antisymmetric, but we build that wave function basing our analysis on single electronic levels. And if you notice, when we evaluated the contribution of the exchange energy, the picture was the electron is described by single electron wave functions. The only thing that changes due to interaction is the energy. So we are translating the interaction of all the electrons with each other. So it's impossible to use a single electron wave function to a problem that is, let's use a single electron wave function and let's transform the effect of the interaction only in a change of the energy. But is this picture correct? This picture is correct only if the effect of the electron-electron interaction is negligible, can be neglected with respect to that corresponds to this relaxation time, can be neglected with respect to the typical electron interaction, typical due to the effect of the collisions of the electrons with other mechanisms that are not the electron-electron interaction. Because the point is the following: if we had found that the relaxation time due to the interaction is smaller than the relaxation time, so if this had been the final result, then the consequence of that is if from one collision due to any interaction of the electron with something and another interaction of the electron with some physical mechanism, the electronic wave function is not stable due to all the possible interactions, then at this point, we may not neglect the contribution of electron-electron interaction, because over one mean-free path, the electronic wave function is strongly disturbed by the effect of the electron-electron interaction. So in this case, no single electron So in this case, the single electron level picture cannot be applied, because at this point, all the calculations we have done up to now, let's say up to the block electrons model, are calculations where we always assume that the single electron picture is fine. So if we had found that the relaxation time due to the interaction is smaller than tau, then that picture is destroyed. So we have to start all the calculations from the beginning by using a different approach. So no Slater determinant, but a full wave function for the electrons, where we consider the number of variables that is equal to the number of electrons. But the fact that the interaction time, the relaxation time due to the electron-electron interaction is larger and larger with respect to the relaxation time that we associated to collisions, let's say, gives us the possibility to use the single electron level picture, so we may keep all the calculations that we have performed from the, let's say, Drude model up to the block electrons. So the final consequence is, for practical reasons, in general, we may neglect the contribution of electron-electron interaction because that is very, very small, both due to the screening and due to the Pauli exclusion principle. So the combination of screening effect and Pauli exclusion principle is such that the effect of electron-electron interaction is negligible and has an associated relaxation time that is very, very large with respect to the relaxation time due to collisions. So this means that from one collision to the next, we may always assume that the single electron level is stable. So we observe no decay of the electronic wave function. And a decay may be observed, for instance, because actually the single electron wave function is not an exact solution of the Schrödinger problem, because the exact solution would be the many electron wave function. So the single electron wave function is not stable in general. But thanks to this qualitative calculation, the instability of the electronic wave function is not so harmful. So that doesn't hamper the single electron picture that we have used up to now. So from now on, we will proceed with single electron levels, and we will just include any effects of the electron-electron interaction just into the energy of those electrons. So the modification will just regard the energy values and not the expression or the actual shape of the electronic wave functions. Okay, so it's nearly 11:30. Yeah, so I think I will stop here the lesson. Do you have questions or comments concerning this part? Okay, so if you have no questions or comments, I stop the registration.